Thank you, Brian. So welcome to part 2 of this webinar. Just to recap what we'll be doing in this webinar. We're creating an introductory example of image classification applied to robotics. So once again, we're going to be starting with the hello world of ROS2, which is the turtle sim, a very simple two-dimensional simulation where keyboard input is used to control a simulated robot. Although very deceptively simple, it still conveys all the concepts that you run into in robotics applications. So we're going to be replacing this keyboard input with camera input. During our last webinar, we used Vitis AI to accelerate a deep learning model which classified the images where we were detecting American Sign Language with our hands. And in this webinar, we'll be integrating this into ROS2 and converting these hand signs into commands that control our robot. So to do this, we'll be using the velocity command, which has data in X, Y, and Z directions for translation and rotation. We'll be using the A for advance, B for backing up, L for turning left, and R for turning right. And we'll actually at the last webinar, we saw that there was also 3 special characters. We'll be making use of those. We'll use the space to clear the lines that have been drawn by a robot, and the delete to reset the turtle sim. So that clears the line and recenters the turtle in the middle of that little screen. So just as a add-on, so this is the agenda of the slides. I will not be going through the slides. I'll be doing this live, but these slides will be available after the webinar for reference. So let me get to since last time, I have posted a new project which covered the final result of what we created in the last webinar, so the ASL classification. So this project provides the pre-built SD card image, including the ASL classification models for the various DPU architectures. And some of the updates that were applied in this new content is I've trained an additional classifier, MobileNet V2, which is 40 times faster than the VGG16 that we saw. I also added support for the dual cam add-on modules, and also added support for the display port. So thanks to Tom Curran for making the display port available on ZU board. So this is done via a add-on module as well. So just a quick overview of the differences between the two models. In the last webinar, we saw VGG16, which is a fairly simple structure, 22 layers, whereas MobileNet V2 has a significantly more complex structure. We have 155 layers, but we have 30 times less compute to perform per image. So it's a much lighter weight model. And we can see in some of the benchmarks, we could use the Xilinx XTP util to perform benchmarks without pre-processing, post-processing. And with this, we get 44 times faster. The files that I provided also have a Python script that perform benchmarks, so with and the pre-processing and post-processing in a batch mode, and this gets 23 times faster. And our final application, as we saw, was only 2-3 frames per second with VGG. So we can see that this upper bound for the frame rate was limited by the model. And then the reason that it's a little lower here is because we have a single threaded Python, and that has its limitations as well. But still very convenient for doing fast prototyping. But for our MobileNet V2, a C++ application will achieve the full frame rate of the USB camera. But for our case, we're still achieving 20 frames per second, which is very, very fluid. So we'll be using the same setup as last time without the dual cam mezzanine. So you can see optionally we have the Oh, sorry. We can have the dual camera mezzanine here as well, but for this webinar, we'll continue without the dual cam mezzanine. So we're programming the SD card provided by this link, which now includes the X models for the ASL classification as well as the scripts. We connect this to our USB-C power supply, connect it to the PC with a USB serial port. We have an Ethernet connection. This is the link on which we forward video using SSH and remote X windows. And we have our video input, which is a Logitech USB camera. So if we just recap on what this looks like, just need to see the address we're at. So we're at 10.0.178. It is root. We just launched this with, and once again, we need to specify the model. So this time we'll be specifying the MobileNet V2 model. We have our B5512 architecture. And we could see that we have our A. There's a few hand signs that are pretty similar. So the A is the thumb on the side, the thumb in the middle, and the front is S. Underneath the fingers is an E. The B will be backing up, L turning left, R turning right, Y, space, delete. Sometimes looks like a Q. So we're getting pretty decent. So here we see we're getting 15, 17 frames per second. When this runs locally with the DisplayPort, we get even faster because we are consuming some bandwidth over Ethernet to get this to the PC. There's no compression going on right now. So that's the ASL classification that we are working with. So now an overview of ROS. Very quick overview. I have some slides covering this, but for the sake of time, I'm going to have to go a little faster. So one place I would recommend to get started is docsros.org. There's versions of the documentation for each distribution. We're using the Humble distribution. And you can see here this is where they cover the topics using TurtleSim. So this is why I'm calling it the Hello World of ROS 2. So there's one picture I want to share, and it's this one here. So the nodes in ROS. So this image conveys quite a few concepts. The concept of nodes. So a ROS 2 application, or ROS 2 graph as it's called, always consists of several nodes. And ideally a node performs one task, either gathering input from sensors or cameras, or processing that information to create metadata, or taking that information and creating decision algorithms such as perception for driving. So we can see here a node will typically communicate with topics. So messages are sent and they're broadcasted as topics. So a node will publish to a certain topic and other nodes will subscribe to this topic. And so since this is broadcasted, many nodes can publish to the same topic, many nodes can subscribe to the same topic. And there's also a different kind of communication, which is services, and these are point-to-point communications. So we'll be seeing each of these cases. So in the case of a topic, when communicating with our TurtleSim, well, when transferring video, we'll be using a topic, and the message will be an image. When communicating with our robot, we'll actually have a different kind of message for that. And to clear the lines and reset the turtle, that's done with the services. So that'll be a slightly different message to do. Another thing I wanted to share is the ROS indexros.org. So since ROS 2 comes with a lot of packages, and if we want to search for certain packages, this would be the place that I would recommend to start. So, for example, if we want a package that will read the images from a USB camera, let's just search for camera. Spell that right, that could help. And we can see there's quite a few of them. And if we go back, you may have seen one that's very popular was CV camera. This was available in Foxy, the previous distribution of ROS2. But since then, it's not available in Humble. So I moved to V4L2 camera, which is the one coming up at the top of the chart. So we could just, check if this is recommended for use. It is. And we actually have a GitHub of the people providing this package. So how normally with a Ubuntu release, all these packages would be installed with apt-get install, but in our case, as you can see with this project, adding support for ROS2, we're doing this with a meta ROS layer. So this is being integrated into the Petalinux. And you can see here, go to ROS 3, we can see that we're adding these V4L2 camera, as well as CV Bridge and Turtle Sim. So these packages are all getting installed directly into the Petalinux project. So as we're running, we already have this running on the board. So if I go back, or ZU board, all right, so to work with ROS, we need to start by calling the ROS setup script. And then we can look at which packages are installed. So there's quite a few of them. We can use grep to just filter out this list. V4L2 camera. You can see it's there. So we can also see the executables, so which nodes are included in these packages. So we can see that there is a V4L2 camera node. So V4L2, by the way, is video for Linux in the V4L2 package, and another compose test. So we'll be using this one here, the V4L2 camera node. So to launch this, we do ROS2 run, the name of the package, V4L2 camera, and the name of the node, V4L2, or the executable. So this communicates with the USB camera driver. There's a few settings that failed, but this does not prevent the USB camera from working. It also looks for a calibration file. If you have that in your system, you can calibrate it, especially for doing depth perception or things like that, more advanced algorithms. So if we launch another session, since this ROS2 run is occupying this session, log in as root once again. And now if we list which nodes are currently executing, we can see that we have V4L2 camera. And we also have this RQT GUI. Okay, so this is running on my other Linux machine. So there's one thing that's nice about ROS2 is inherently, just display some environment variables. You can see that we have ROS2, distribution humble, Python version 3, and localhost only is 0. That means we're not keeping the communication between nodes local to our platform. We're actually exposing them out to the network. So my other machine can actually see the output from this V4L2 camera, and I can display it. So I don't have that connected up to this webinar, so we can't see that. But that's what this one's all about. So it's a node on another system, and there's also a way to limit the communication to certain groups. That's another environment variable that can be used. So ROS2 inherently has the networking support, which is very convenient. If we list the topics, so we see we have ROS out will always be there. Parameter events are topics that notify the nodes that someone has changed their parameters. So image raw is the one that we're interested in. So this is the camera video being sent, and camera info is additional information about the camera. So if we get more information about this image raw, you can see it's a message of type sensors, sensor messages, message, image. So this can actually be found in the documentation online, and we can see that this message, so we have a header, we have the width and height of our video data, we have the encoding. So this could be RGB, BGR, YUV, the color format, and depth of each component. Is the data big endian or not? In our case, it's 8 bits, so it's just bytes, so there's no ordering to specify. And the actual data. So if we look, we can actually echo this information. Oops, spelling. And I'll just let this run for a while and stop it. And then we can go look at the header, because it's kind of meaningless to look at numbers unless we have an image viewer. So we can see that we have an image of width 640 by 480. The encoding is RGB, 8 bits for each component. And the step is just the width between each, in terms of memory storage, width between each frame in the memory. So with this, if we go back to our adding support for ROS2, I describe in here how to create a simple ROS2 graph where we create a publisher and a subscriber to implement a video pass-through. For this webinar, we'll only create the subscriber since we already have a publisher of video data running. We won't need to do that. So if I go back to my slides, I'll just show a diagram of what we'll be creating. So these are the slides that you'll have available for downloading. All right, so in the project we created in Python a publisher and a subscriber, but in the webinar we'll be reusing this V4L camera, V4L2 camera, which is already running, and exposing a topic called image raw with a message type of type image, and we'll be creating this USB camera subscriber. So how do we do that? Well, believe it or not, let's use ChatGPT. So write Python code for ROS2 subscriber node for video. And for these simple type of examples, it's actually a very good resource to use to start. So a few things in the code we can see. Okay, I don't like this. I wanted to use CV Bridge. Okay. Okay, that's more like it. So we can see here it's using a Py template. So this is just standard ROS2 infrastructure. We have our CV bridge. So what this is, it converts between OpenCV data structures and ROS2 messages. So that's important. And we have here the sensor messages containing the definition of our ROS2 message. And of course, we're using OpenCV2 to do the video capture and some format conversion. So we can see here it creates a class. On initialization, it creates a subscriber with this name, video topic. We'll be changing that. It's got the encoding. Interesting. Okay, I'll be changing this as well. So let's copy this code and go back to our session. All right, so now we want to create our workspace. Make webinar workspace. Create a source directory. And we'll create a package, a ROS2 package using a template. So this is ROS2 package. Build type. Package create. Build type. I meant Python. So it's a Python template. There's also C++ templates, and we're going to call this PyVision. So Vision, because it's the ZU1 Vision webinar. Py, just to distinguish that this is a Python package. We could maybe in the future create a C++ version of this same example as well. So this creates a directory structure here. We'll actually update this. See, I've got a solution in case things go wrong, but this is the one that was just created. So in our source directory, we have PyVision. We have these three setup files, setup.py, config, and package.xml. And this is where we have our source files. There's nothing in this init.py right now. There's nothing in this resource file either. Anyway, 0 bytes, it's empty. There's a various test scripts here. This is just standard infrastructure if you want to do unit tests on our package. But if we create a new USB cam subscriber Py, copy the code from. I'm not actually going to change this to RGB because we saw that. I don't know if you recall when we were looking at the messages, we saw that the encoding was RGB8. So let's set this to RGB8 just to make sure we're compatible. RGB8. We want to call this image raw, because we want to subscribe to the same topic as being published. That's about it. So we save that, and then we go to our setup.py, and we add a console script. So this will be USB cam subscriber equals PyVision or package dot USB cam subscriber or Python script, and there's a main function in there, so we'll be referring to that. We save that, and we also need to add which packages we're using. So test for the execution, we'll have a few of these. So we need to add our RCL I. This is all based on what we have in our code. We have our standard messages, our sensor messages, our CV, bridge, course, our OpenCV library. Okay, for this, it's actually spelled OpenCV. All right, so in these package.xml and setup.py, normally you want to update these versions, who you are, your email, a meaningful description of the package, and which license you're making this available as. So, for example, the Apache 2 license. So we won't do that now for the sake of time, but if you're thinking of releasing this package, it's good to fill in your information. All right. So to build, it's as simple as, okay, we created our package. Let's just see if we can see this package naively. And it's not there. So that's because we need to build it. So to build ROS2 packages, there's a build tool called Calcon. So we do Calcon build. Okay, I got this wrong. Exec depend. Bad memory. Let's change all these. Try to build that again. All right, so if we try to now see if our package is there, it's still not there, and that's because for these local packages, we need to install their installation script. Now, if we look at it, okay, so now ROS2 can see a USB cam subscriber node in the PyVision package. So to run this, recall that we have our V4L2 camera still running in this terminal. So now we're going to run in the PyVision package, our USB cam subscriber. All right, we can see we have a video pass through. Now the colors don't look quite right. Okay, so I know what that is. That is, go back to, if anyone's familiar with OpenCV, you know that OpenCV uses BGR ordering. But I want to keep this RGB because we'll be connecting this to a deep learning model, which it supports RGB format, so we want to keep it like that. But just for our image show function, we need to convert this to BGR. So this is done with the CV2, CVT color, CV2 color, RGB to BGR. And we want to display this version of the image. So if we rebuild that, and we run it, all right, so that's got the correct colors now. All right, so we're all set. Another thing that we may want to do is, I'm just going to go back to my script. I need to add some files in the setup.py. I'll explain why I'm doing that. All right, so we're telling it, in addition to having the source files, we want to include launch files. So this just makes it more convenient because, as you saw here, to get a very simple ROS2 graph with 2 nodes, I had to have 2 terminals open. And that, if you can imagine a ROS2 graph which has hundreds of nodes, we're not going to open hundreds of terminals to launch our application. That wouldn't make sense. So there's this mechanism called launch files, where we could launch all the nodes from the same place, and that's what we'll do. So this line is basically telling the ROS2 build tools to look for all the launch files in the launch directory, which end with launch.py or YAML. So we'll do that, and we'll create a launch directory. Create our launch file. So USB cam pass through launch.py. Just go back to my script. Copy the code in there. All right, so this is essentially saying we want to launch 2 nodes. The first one is the this is the one from the original master project. So we want to run one with V4L2 camera node, the V4L2 camera package, and our USB cam subscriber from our PyVision package. All right, so let's stop this and rebuild our package to include this launch file. Just rerun that local setup script. All right, so ROS2 launch, name of our package, and name of our launch script. So USB cam pass through launch.py. All right, so we have the same result, but from a single point of launch, that launch file. All right, so now that we have our basic infrastructure, let's go back to our slides. We're now going to be adding our ASL classifier, like so. So instead of having our USB subscriber here, we're going to create a new node called webinar demo. So it will essentially be doing the same thing, displaying it on the monitor, but also publishing an image at the output. So in this case, it'll be the same image as the input, but overlaid with some graphics of what sign has been detected. So we can do this with ChatGPT, right? Python code for ROS2 subscriber publisher node for video. So you can see in this case, it's a video processing node that it has a subscriber, but it'll also publish a message that's been processed. So in this case, the template doesn't do actually any processing, but now, so this is our basic template. But adding the Vitis AI model is a little more involved. So what we're actually going to do, for the sake of time, we're going to copy from the solution and put that in our directory. So go see this. You can see our code is there. We can have a look at this. So now this actually has the ASL as well as our robot control, but we're just going to look at the ASL classification for now. So there's a bunch of supporting functions. One that I want to point out is this get DPU architecture, where I call the XDPU utility just to get the DPU architecture. So recall from the first webinar, if we do that, we'll get this line specifying which DPU architecture. So it's the B512. So in this script, I'm looking for the line that has DPU architecture and extracting the number that's after the B here. So I'm taking the second result of this search string and then putting back the B to get that B512 architecture. And then I'm creating the full path. So we don't need to specify the model. It'll automatically detect the model and use that one. And it assumes that it's in the home root ASL classification by DCI. If this is different on your system, you can change this. And then there's some preparation. We're getting our region of interest, which is that green box in the middle. There's some pre-processing to the model. So we're just normalizing between 0 and 1. Sorry, I got that wrong section there. Right here, the pre-processing. This was the post-processing. So for the 29 probability outputs, we're looking for the one with the maximum value and to get the index of the hand sign that we're looking for. And then, so that's basically it. We'll just run this for now. So I'm just going to rerun our camera node, V4L2 camera node for now. Oh, I forgot to add that webinar demo script. Webinar demo equals I vision webinar demo main. Do that again. So ROS2 model package executables. Let's look at packages visible. There it is, webinar demo. So we want to launch that. ROS2 run by vision webinar demo. See, detected the B512. That happened very quickly. So we essentially have the same effect as our previous ASL classification. So now in this one, I'm also displaying the from the 4 commands, the advance, backup, turn left, and turn right, in addition to the detected letter. So if we have like other types of letters like our E or S, that should not translate. Yeah, sometimes you get false detections on that. The S or the Y, letter Y doesn't have a command associated with it. That's that. And now if we go back to our source, we're also going to publish a twist command. So twist commands, let's go back to our webinar. All right, so controlling our robot. So we created this. We already saw this part where we were publishing the modified version of the image as well as showing it with image show. We're also going to publish a twist message with the name turtle1 command velocity because it corresponds to the name of the topic that turtle sim is subscribed to. So what does that twist message look like? It's actually 2 vectors of size 3, one for linear movement and one for angular movement. So it's linear translation in the X, Y, and Z directions, as well as angular rotations in the X, Y, and Z rotations. So for our 2-dimensional simulation, this frame of reference is always with respect to the turtle. So wherever the turtle is, if we put a positive value on the linear X, it will advance regardless of where it's facing. And if we put a negative value, it'll back up. And to turn left and right, that'll be on the Z axis here. So turning left, counterclockwise, turning right, clockwise. So positive and negative values on there. And for the space and delete commands, this will be using a different format. So the services communication, and this is, the code's a little more involved, but I'll let you refer to this if you want to. We'll concentrate on these, on the actual actions of movement here. So to run this more efficiently, we'll want to add another launch file, webinar demo launch. And I'm just going to copy the content here. So we're going to keep the same input. We're going to the second node will be our webinar demo, and the third node will be our turtle sim. Turtle sim node. All right, so stop this. We'll rebuild the package. And rerun webinar demo with our launch script. So this will launch 3 nodes. V4L2 camera. Looks like I spelled that. Webinar demo. How do I spell that? Oh. Probably need to rerun the installation script. Right. It's a Python script, not a shell script. There. All right, so V4L2 camera, webinar demo, and turtle sim. So this is the demo we've been building up to. And we can see that now we can advance our turtle, we can back up our turtle, we can turn left, turn right, and this kind of like illustrates the notion of why you'd want to be doing things in simulation. For this simple example, we've hit a wall, so we hit the top of the simulation environment. So in this case, it's just giving us a message, but in a real robotic application, this could create damage to very expensive equipment. So that is why in ROS2, it's very common for people to work in simulated environments. It saves costs for the developers. You don't need to reproduce your robotic equipment at every development post, but also it ensures that you can do some minimal verification with your algorithms before trying them on actual hardware. So this one's actually a little hard to drive. So there's a little modification I want to do just for fun. When we're turning, instead of just doing a rotation on the x-axis, we can also advance. And this makes things, I found, a little more easier to control. And it also creates an arc. So the turtle advances while turning, so that creates an arc. So if we build this and rerun it, Let's see now, if we do our turn left sign, just actually draw a circle. If we advance, turn right. So, and I mean, it's endless. You could play around with this, change the commands. Maybe the turtle sim also publishes its position, so you can do the movement based on its position just to improve the control process. So essentially driving this turtle around. Maybe you can have the turtle look at its environment and control itself. That would make the turtle self-driving. That could be interesting. But that's it. So that's what I wanted to show you. So a lot of things that are capable with the Vitis AI and ROS2 on the ZU board. Get my thank you slide. There you go. Thank you very much.